discuss about the work done during the constant force as well as work done during the varying force. In the both cases, we discuss about various different cases which is observed in that when we apply the constant force or a varying force. In that varying force we are using the spring. So by using the spring, in that condition the force will be always acted in the opposite direction, opposite to that displacement. So all these cases will be explained in our previous lecture. Now in the present we are discussing one more concept, which is the conservative force and the non-conservative force. When you say the force is conservative, so if you apply the force to any object, we are considering the one object, and apply the force to that object, then this object will be displaced. So this object will be displaced from one position to another position. It may be along a straight line or it may be along the curved path. So if this movement or this motion, we can say that in that the total work done in that moving conditions of that object. Here in this example, when we apply the force to that body, then the total work done of that moving object is given by, we can determine this W is equal to integration from, here we are considering this object which is moving from place A, one position to another position, so we can simply say that from position A to position B. So if you apply this force F, if you apply this force F to that object, and this object will be displaced with the distance dr, and the integration of F dot dr from position A to B, it gives the total work done. So in general, in this work done, we can see that this work done will be depends on the nature of that path. So if you consider in general case, this work done will be depends on the nature of path. This object which is moving from one place to another place, or here from A to B, which along the curved path, so this work done will be depends on that path. In some cases this work done will be not depends on that path. So from these two factors we can categorize our conservative force and non-conservative force. So if this work done will be depends on the path, nature of path, basically that object will be moving from one position to another position. If you apply the force, then this object will be moving from point A to B. So if this force, if this applying force is independent on that path, this applying force is independent on that path, then such force we can say that the conservative force. Here we can say that this work is, or this force is conservative force. If this work done depends on that path, this path A to B, or simply we can say that, let's just consider that the particle which is moving from point A to B. Here we can define the point A, here point B, or we can say that position B, second position over. Okay, so from A to B along the curved path, so we can define yeah, we can say that this is path 1, this is path 2. From A to B along the path 1, or this object, this particle will be moving along path 2nd. It may be a straight line or any other way along any curved line. So if this object is moving along the path 1, path 2, path 3, path n, which is depends, if this work done is depends on this path, then we can say that the force is non-conservative. Here, then we can say that the force is non-conservative. And if this work done will be independent if this were done independent on the path, then we can say that the force is conservative. Force is conservative. Okay, there is a simple relation. If the path, this burden is dependent on the path or independent on the path. If it is independent on the path, then we can say that the force is conservative force. Okay, so we are considering again from this figure. Again we are consider the particle here. We apply the force. This object, this particle will be moving from path 1. If it is moving from along the path 1, we can define here. We can define this burden, or we can say now we can say W1, which is moving from path 1, then from A to B, F dot dr along the path 1. Okay, which is along the path 1. If this burden or this object moving from along the path 2nd, then we can again define the burden which is along the path 2nd from A to B. This object moving from this curved line which is path 2nd. In that condition, again our burden will be W2, which is nothing but from A to B. Same, applying force, and there will be the some displacement. Okay, it is a vector quantity which is path 2. This is work done W1 along the path 1. This W2 which is again the work done along path 2. Now if you consider here, if you consider W1 is equal to W2, if you consider W1 which is equal to W2, it means that the work done along the path 1 which is same as the work done along the path 2nd. Here this W1 is equal to W2 gives, or we can say that the work done along the path 1 which is equal to, or which is similar to the work done along the path 2. Okay, so in this case here, if it is same, we can say that the force is conservative. Here when you say that, then this F is equal to conservative force, and in this case the work done on this particle by applying that force, this work done by application of that force, which is this force is independent. So here this W1 is equal to W2 gives, or we can say that the work done along the path 1 which is equal to, or which is same, the work done along the path 2. So here we can say that this force to moving that object, this force which moves or which changing their position from A to B, from A or from path B, this force is conservative. Here we can define this force is conservative. Okay, one more thing here, we can say that in this case the work done between that particle, okay, if you apply the force which is independent on the path in the conservative field, this work done, this force is independent, or this work done is independent on that path. So this basically here the path which is followed by that particle is between these two end points. So here this work done by that force which is independent on that path, which is independent on that path, but which is depends on that end position, which is independent on that path, which is path 1, path 2, or any other path we considering. So this work done by that force which is independent on that any curved line, but which is depends on the end points, which is point A and point B. So in that case it is depends on only the end points. Now from this all overall explanation, we can define or make a small definition of that conservative force. So we can defining this force. The force is called the conservative force. When you say this force is conservative, if the work done, if this work done, here we can directly say that W is equal to integration from A to B F dot dr. So the force, we can say the force is called the conservative if the work done by that particle, the work done by that particle is moved from one point to another point. This particle move from one point to another point depends only on the position, which depends only on the positions. Okay, yeah. So I'm again repeating the definition. A force is said to be called, or a force is called the conservative force if this work done, by that particle that move from one point to another point, from one point to another point, which depends only on the position, not on the path followed by them, not depend on the path which followed by that particle. Okay, so it is simple definition which is only mentioning that this work done only depends on that end position, not on the path. Okay, so here we are considering again. Here the work done which is along the path 1, which is nothing but W1, which is equal to from A to B F dot dr. Here now just consider the work done which is moving that particle from point A to point B along the path 1. So in that condition we can say that the work done is equal to W1, which is nothing but from integration A to B, which we can say that the particle will be moving from point A to point or position A to position B with application of this force. With application of this force, changing their position small dr. So in that along the path 1, work done is W1. Here we are considering the work done in the path 1. So the particle will be moving from point A to B along the path 1. In that condition, the work done will be W1. So W1, which is basically from A to B F dot dr. With the application of this force, there will be body. This particle will be displaced from or moved from position A to B along the path 1. So this is for path 1. Okay. And if you consider it, the object will be moving from B to A. This from B to A along the path 2nd. So we can say that the total this work done will be W2 dash, which is from B to A. From B to A. Again we apply the force to that particle. This particle will be moved from position B to A. And in that case, here the path is 2nd. So again work done is equal to W2 dash, which is nothing but integration from B to A F into dr. So this is from path 2. Okay, so from A to B, from B to A. Here we can considering the total work done, because here we can check the round journey, or we can say that the closed loop from position A to B along the path 1, again from B to A along to path 2nd. So from here we get total work done W is equal to W1 plus W2. So from here W2 dash. So W1 plus W2 dash gives the total work done for this round journey trip, or we can say that this closed loop from point A to B. If you consider the work done, here we can consider the work done from position A to B along the path second. Here we are considering the work done from B to A along the path second. Now I am saying that the work done for the, if you apply the force and the body or this particle will be moved from A to B along the path second, then the work done will be W2. Then the work done will be W2 from A to B. A to B with application of force. Okay, which is along the path second. But here you know that here, I will clean here, and you know that this W2 dash, which is nothing but, from these two equations we can say that this W2 which is equal to W minus W2. We can say that this W2 is equal to minus W2. Then your total work done will be this. Here our total work done will be W1 minus here W2 dash, which is nothing but W2. So this is total work done. This is the value of total work done W, which is equal to W1 minus W2. But we are considering the conservative force, and in that conservative force you know that W1 is equal to W2. This force, if you apply the force on that particle, the particle will be moving from A to B, which is independent on that path, which depends on the positions. So in that condition, W1 is equal to W2, and the total work done, which is equal to W1 minus W1 or W2 minus this, because of that condition W1 is equal to W2, you get total work done will be 0. Here you get the total work done will be 0 in that round journey or in that the closed loop. Again we can define this conservative force. You get another definition. So we are defining from this W. So from this W we can define the conservative force. So if the particle is moving under the action of that force, the particle is moving under the action of the force such that the total work done, this total work done of during the round journey trip, or we can say that this closed loop, we can say that the closed loop or closed path, which is equal to 0, So simple definition of that conservative force in term of your here we get the simple definition. We can say that if the particle which is moving under the action of the force such that the total work done during this round journey trip, during from A to B, B to A, from path 1 to path 2. So in this round journey trip or closed path, the total work done will be 0. So this is your simple conservative force. If you want to check some example, we can say that the gravitational force, also the Coulombic force, in the Coulombic electrostatic force, both are the examples of conservative force. Both are independent on the path, depends on the end points, point A and point B. So both are the simple example of that conservative force. Here, to here we consider the example of that conservative force. Just now I explained that the gravitational force or the Coulomb electrostatic force, both are the examples of this conservative force. We just check for the gravitational force. So for that we are consider, if you consider the gravitational force, we have to consider the two massive bodies. So we are considering the two massive bodies. Okay, so one massive body which is having the mass m. Yeah, okay. One body which is having a mass m, another body which is moving, or we can say that this is at originate from origin O, and here the second another body which is having a mass small s, which is moved from point A to B. So we can considering here the point A and here the point B. So the second body will be moving from point A to B. Okay, so along this path, or we can okay. So this is point A, this is point B, and the second body which is having a mass small m, which is having a mass small m, which is moving from point A to point B. So just now we will explain about the gravitational force or the Coulombic electrostatic force, which are the conservative force. So we are taking the one example of that gravitational force, which is we are proving that this gravitational force is a conservative force. If you considering the closed loop or their closed path journey, or we can say that round trip journey, then their total work done will be 0. So here we are considering for that gravitational force, there are two massive body, which is one body which is at origin O having a mass m, capital M, and this another body which is from that origin to, which is moving from point A to B with distance r. This body will be moving along the path 1. Here we are mentioning the path 1 from point A to point B, or position A to position B. So here these two massive body, we are considering the two massive body, and here we are checking if the body which is moving from A to B under the effect of that gravitational force which exerted by the mass m, which is exerted by that mass m on that small body which is having mass small m. So here we have to calculate the work done. So this total work done by the gravitational force here from that two massive bodies. So the total work done by the gravitational force which is moving of the body mass m through the small displacement d. This body we are considering this small body, or the body which is having mass m will be displaced with because of that the force which is exerted by that mass m. So it will be displaced with a distance ds. So we can defining the work done dw, which is equal to, this is by with the application of the force F dot ds. So we define this dot product F dot ds, which is nothing but F ds cos theta. It is F ds cos theta. Simply we can calculate the work done from this concept. the body which is one body which is moving and the exited this force by that body M. So we get from this geometry here this small body which is moving along the path 1. So we can define here ds cos theta, which is nothing but the small dr. Here you get from the geometry we can write the ds cos theta is equal to dr, and we can put this ds cos theta is equal to dr into our equation of that work done, total work done. So this w is equal to f into dr. This is f into dr. So you get the work done, the value of that work done. Now here the gravitational force, here the gravitational force which is exerted by the body M on the body M, which is moving from A to B. So the amount or the magnitude of that force, which is nothing but, here I write F is equal to, it is F is equal to G M divided by R square, which is masses of the two massive bodies, into R, which is nothing but the distance between the separation, the distance between these two bodies. Okay, so we can put the force, the value of that force, dW is equal to G M divided by R square into dr. We just put the value of that force, gravitational force. So in that, during this work done, the work done in a moving body from point A to point B. So we can write, here we can write total work done, which is nothing but from path 1 from A to B. From A to B, G M divided by R square into dr. From G M divided by R square into dr. Here from this G M are the constant value, we can take common out and write I'm writing here W, which is equal to G capital M small m into from A to B 1 upon R square into dr. So to calculate or to determine the total work done, we have to integrate from A to B 1 upon R square dr. So this value of that integration, you get the total work done. And from A to B, this particle or this body which is having mass m moving from A to B. So we can write the work done from A to B, which is nothing but G M into G M into 1 upon R square, which is nothing but minus 1 upon R, from A to B, from A to B. So the value of that integration becomes G M. We are just putting the value from A to B, this object here which is moving from point A to B. So the value which is RA and RB. Here it is RA, and for the point end point B, which is RB. So you get G capital M small m into 1 upon RA minus 1 upon RB. This is the work done from A to B. From A to B. So this work done, which is moving body, which is along the path 1 from position A or point A to B. This body which is having a mass m. And in that condition, from this equation it is clear that the work done of that gravitational force, this work done of that gravitational force which is exerted, the force which is exerted by the mass m, this body which is having mass m is, or which is independent on the path, which is independent on the path, or which is depends on the end point. So this is W is equal to A from A to B is equal to G M1 M into M bracket 1 upon R minus RA minus 1 upon RB. So this is the simple work done. This is the work done in a moving body from of the mass M from point A to B. This is the total work done of that body which is having mass M from position A to B. Here, from this equation we can see that this total work done, or it is simply clear that the total work done by that gravitational force in a moving body, in that moving body, is basically depends only on that position. It is only depends on the end position, point A, position A and position B, and it not depends on that actual path, which is path A, or if you consider a path B. So here simply clear that this work done only depends on the end position. Similarly, if you consider the path second, or from B to A, if you consider from work done B to A, which is nothing but which is equal to G M divided by or into 1 upon RB, you get 1 upon RB minus 1 upon RA. If you consider the body of that having mass M will be moving from position B to A, which is along the path second, which is this path from B to A, using the path second. In the first case we are using this body M, which is moving from A to B along the path A. Now we are considering same case, this body which is moving from B to A, but path is second path, or that second path you get G W total work done, W from B to A, G capital N small m into 1 upon RB minus 1 upon RA. And here if you consider the total work done, here we consider the total work done, which is nothing but in that round journey or in the closed loop. If you considering this closed loop, then you get WA to B plus WB to A. This total work done is nothing but WAB plus WBA from position A to B, path 1, from the work done from B to A, path second, and from A to B, B to C, path 1 to path second. It gives the round journey, and in that round journey the total work done is 0. As per our definition, we can see that the total work done of that round journey or that closed path loop, you get the value of that work done is 0. So again we can define, or we can say that the work done in that moving condition or that moving object having a mass m under the effect of the body capital M, or we can say that effect of that gravitational force. It is effect or exerted the gravitational force along the closed loop, or the round trip journey, get the total work done is 0. Again here you get, in this example we are considering the example of gravitational force, and in that gravitational force, this round journey or closed path loop, again you get the total work done, which is again